This presentation will discuss Anova analysis, which can be found in your textbook in Chapter 13. A couple of basic terms involved in Anova analysis are factor, treatment, and experimental unit. A factor is like the independent variable that you're investigating. The treatment are the things that have an impact on the independent variable, and the experimental unit are the observations that you select to test the treatment on the factor, or test the impact of the treatment on the factor. Here's an example. AutoShine Incorporated is considering marketing a long-lasting car wax. 3 different waxes, types 1, 2, and 3, have been developed. In order to test the durability of the waxes, 5 new cars were waxed with type 1, 5 with type 2, and 5 with type 3. Each of the cars was then repeatedly run through an automatic car wash until the wax coating showed signs of deterioration. Use the results of this study to determine whether or not the 3 waxes are equally independent. So our factor here is the effectiveness of the wax, and the treatments are the 3 different wax types. So we're investigating is the effectiveness of the wax different based on the different types of waxes that we have. This is a single factor ANOVA. So we're testing the equality of 3 or more population means. Our hypothesis, since we want to know, are all 3 waxes equally effective? Our hypothesis then, following the single factor methodology, would be the equality of all of the population means. In other words, the average length of time it takes for the wax to wear off should be equal for all 3 of our waxes that we're using. Now, if we had more than 3, we would just continue on. So you see the general HO would be that the means are all equal. In this case, it's mean of max 1 equals mean of wax 2 equals mean of wax 3. So the average amount of time for each wax should be equal. So if HO is true, then the means are equal and they're all following within one normal distribution, versus our second picture there shows that the means are not equal. In other words, HO is false, and those means are all actually taken from 3 different distributions. So this test is performed using the single factor ANOVA analysis in Excel. So you will go to Data, Data Analysis, then select Single Factor ANOVA, and you will see this come up. You will input your data in the input range. It can be grouped by either columns or rows. So just look at the way your data is set up. Remember to check off if you do have labels in your first row, and that is beneficial because it makes sure that we maintain the integrity of our data, meaning that we include all of our observations and that you know what data is actually being reported. Put your output range on the same worksheet, a new worksheet, whatever works best for you, and then click OK. So here is the actual data from our waxes. We want to test the hypothesis that each of the 3 waxes lasts the same amount of time, so that the mean of wax 1 equals the mean of wax 2 equals the mean of wax 3. So that's going to be our HO. So I will go into Data, Data Analysis, Single Factor ANOVA, and I would select this data from wax type 1 down to the 31. So I would select that matrix of data. And here's the resulting ANOVA analysis that it gives me. All I have to do is look at the p-value. If the p-value is less than 0.05, then I reject HO. Here the p-value is 0.41, which is definitely not less than 0.05, so I do not reject HO. There is insufficient evidence to conclude that there is a difference between the waxes. That's it. Now, if we want to look at something a little bit more complicated, let's say we could look at a 2-factor ANOVA without replication. This is used when you want to examine the effects of 2 or more different factors. It tests the equality of 3 or more population means after a second factor is taken into account. So we're still testing the idea, are the means all equal? In other words, are these observations all drawn from that same probability distribution, which we would find if HO is true, versus they're drawn from different probability distributions, which we would find if HO is false. But here, we're taking two things into account. So two different factors. So let's look at an example. A survey was conducted of hourly wages for a sample of workers in 2 industries in 3 locations in Ohio. Do differences exist in both industry type and in location? So now you're not only looking at which industry they're in, but you're also looking at where they are in Ohio. So now we have multiple factors, industry and location. So here's our data. We have 2 different industries, 1 or 2, and 3 different locations, Cincinnati, Cleveland, and Columbus. And here is our data. So to test this, I would go into data, data analysis, and select 2-factor ANOVA without replication. And here you can see my resulting p-values that it spits out. So again, I'm going to follow my same basic logic. If my p-value is less than 0.05, I reject HO. If my p-value is greater than 0.05, I do not reject HO. So I would not reject HO for the interaction term and factor A. So factor A here was that mean wages do not differ. I'm sorry, factor A here is location. Factor B here is industry type. So what I'm seeing here, wages do not differ by industry type, but they do differ by location. And the interaction between the two is insignificant, meaning it's not always that you see people earning more in industry 2 if they happen to live in Cleveland, or less in industry 1 if they happen to live in Cincinnati. That's what that interaction term would be looking at.